Okay, welcome back. So we did the review of sampling and quantization, all the basic stuff, and that leads us to the combination of sampling and quantization is A to D conversion. An A to D converter is defined by the rate at which you sample, the number of levels into which you cut up your range, or first of all the range, okay, the number of levels into which you cut up your range, and that is usually an integer power of 2, okay, and when you have this, it is known as an n bit A to D converter, okay, because you need n bits, n binary digital numbers to represent 2 to the n levels. So this also gives you the size of LSB to be Vref by 2 to the n, okay. So you apply a voltage V in, and you have a clock running at the sampling frequency Fs, and what happens is at every 1 by Fs seconds it puts out a digital number D out, which tells you in which segment the signal is, okay, whether it's between 0 and 1 VLSB or 1 VLSB and 2 VLSB and so on. So that number is given by D out. And there is also some voltage Vref that defines the range of the input, okay. So these are all the things that you need for an A to D converter, and typically if you buy an A to D chip, this part is inside the chip, you apply a clock from outside, you apply the input and you will get D out, okay. And we already saw that if you apply a full scale sine wave to this, full scale means the maximum sine wave that you can fit into this range, then your signal to noise ratio will be 6.02 times the number of bits n plus 1.78, okay. Well, it could be outside also, it could be inside. So many chips have it inside, and also many chips have the facility that you can override it from outside, okay. Yeah, that's correct. There is not a lot of freedom to change it, but yeah, many chips have it so that you can also feed it from outside, okay. Many chips have it defined inside. So this shows a typical quantizer characteristic, and the left side is the characteristic I have been using. For 0 input, I have 0 output, okay. It's basically a rounding function, right? Between minus half and half, I get 0. Between half and 1 and half, I get 1 and so on. Now, what is the range? The range of the quantizer is the range where the error is less than VLSB by 2. That's the definition, okay. It's assumed that the quantizer here, for instance, after 7, it stays at 7, the output, okay. Apply an input of 7.5, the error will be half VLSB. But if I apply something beyond that, the error increases. So I will define this to be the range. Similarly, when you have a large negative input, this doesn't step further. It keeps going, because it keeps going, it keeps keeps the output at 0. Okay. So this is because of the limitations. Simply as an amplifier has some voltage limitations, the output cannot go on increasing. An OPAMP will have swing limits defined by the power supply. This will have swing limits defined by the number of digits. Okay. So if the quantization error is less than half VLSB, then it is known as no overload range, and beyond that there is overload. So that is the range here. Now I will make a small modification to this, because see, now the range becomes from minus half VLSB to plus 7.5. I just want to work with positive numbers, so I simply move the whole thing by half VLSB to the right and also to the top, okay. So that's all I'll do. Okay. So I just shifted the levels. Okay. So this is just for convenience. The maximum peak to peak error will still be VLSB. Okay. So by the way, I've been talking about quantizers here. Here this is just a quantizer. There is no digital conversion to digital. The input is a voltage, the output is also a voltage. I just cannot have all kinds of voltages at the output. I can have only these discrete levels. Okay. So this is what I have on the left side. On the right side I have the y-axis. As you see here it is voltages and here it is numbers 0 to 7. Okay. I'll say that the number 0 corresponds to the first segment, number 1 corresponds to the second segment, and so on. Okay. And this is the relationship between the input and the D out, and there will be some quantization error added to it. Okay. And also because I moved the characteristics, there is a half VLSB shift. So this I will generally ignore. It will not make any difference to the actual property of the A to D converter, but you should keep this in mind because you shouldn't worry now suddenly the quantization error has increased. No, that's not the case. So there is some offset, that's all. Okay, and the sole reason I do it is because I want to just work with a positive range. Okay, so when I'm discussing A to D implementations, it becomes a lot easier. Now if I want to find out what D out is in let's say MATLAB or something, I can simply use this operation. The floor is like rounding. It's one of the mathematical operations. There's floor and ceiling and round, right? So here I can just use floor. Okay. So if you want to simulate an A to D, but not at the circuit level, you have not yet designed the circuit. You want to see the characteristic or whatever I said about distribution of quantization error and so on. All this you should simulate and verify because that's the only way it will actually stick on, right? Whatever I say, it could be false also. So you should verify it yourself. And the easy way to do it is you use one of these rounding functions in MATLAB that will give you quantization and then you can do that. Okay. So these are just some definitions of terms. Now if I do that, so I will use V out to be floor of V in divided by VLSB. I will get something like this. Okay. So let me write it on the journal. That's probably easier. It is like this, and the input is a voltage, and I have normalized it to VLSB. Okay, and this is D out, and if I want a voltage output, I simply multiply the output by VLSB. Okay, if I want to imagine a voltage output, this is not something I do. It's just to calculate the quantization error. Quantization error is the difference between the output and input. I can't subtract a voltage from a number. I have to also convert the output to some voltage. And I'll simply multiply D out by VLSB. Okay, 0 to VLSB and so on. If I want a voltage output, this is what I'll do. I'll simply multiply it. Okay. To 7 VLSB. Okay. And I compute V in minus V out. What will I get? What is V in minus V out for V in equals 0? 0. And what happens after that? Huh? I want to plot V in minus V out versus V in. Okay. What will the plot look like? It will, as V in increases, you can see here, as V in increases, V out is not increasing. So V in minus V out will simply increase with a slope of 1. Okay. And then what will happen? It will keep on going. At Vin equals VLSB, the output jumps. So this curve also jumps. It becomes 0, right? So this is what happens. Every time there is a jump in the characteristics of the A to D converter, there is a jump in the V in minus V out. Okay? And between the jumps, it will go with a slope of 1. Okay? So this voltage I call VQ. When V out is jumping, it will follow the jump in V out. When V out is not jumping, it will simply follow V in. Okay? So this is just a definition that is easier to handle when we come to other types of converters. That's why I do this. So something like this. Okay? What is the maximum value? Huh? VLSB by 2? Why? What is the maximum value here? See, when it is just below 1, the input is VLSB, right? Almost VLSB, and the output is 0. So the maximum value is VLSB. Okay. The only difference is before it was going from minus VLSB by 2 to plus VLSB by 2. Now it is going from 0 to VLSB. That's why I said there is no fundamental difference. But sometimes you will see this representation, and sometimes it is also easier to describe some A to Ds when you have everything positive. That's all. It's only so this VQ goes between 0 and VLSB. That's all. The only difference between this and the quantization error E I defined earlier was a shift of VLSB. Okay. I mean, I'm going over this because I will show characteristics which have only positive parts, but don't imagine that the quantization error has suddenly increased. It's still, the range is the same. It was going from minus half VLSB to plus half VLSB. Now it goes from 0 to VLSB. That's all. The total range is the same. Okay. So if I want to relate this VQ to the E that I defined before, I have to translate it by this much. That's all. And this is the type of characteristics you will see in the data sheets also. So just for you to be able to interpret it correctly, I am going through these terms. Is it okay? So when I have an n bit A to D conversion, I have 2 to the n possible levels at the output. Okay. So in this case, the characteristic shows how many bits? Characteristics here, how many bits is that? 3 bits. There are 8 possible levels, 0, 1, 2, 3 up to 7. How many jumps will you have? 7 jumps. Okay. You have numbers from 0 to 7, and between each pair you will have a jump, so you have 7 jumps. So in general, you will have 2 to the minus 1, 2 to the n minus 1 jumps or comparison thresholds. Okay. Now, how will you implement the A to D? I mean, just by looking at the characteristic, what will I do? For every jump, I have a comparator. I'll see whether it's more or less than that jump, and then decide what the output should be. Okay. That gives us the most basic type of A to D converter. Okay. Is this fine? Now what happens in a real A to D? So you wanted to have a jump at 1 VLSB, and it turns out because of some errors it is slightly greater than 1 VLSB. Okay, as you see here. Now second jump should have been at 2 VLSB, it happens to be at less than 2 VLSB. The third jump happens to be exactly at 3 VLSB. And the fourth one is shifted to the right by half VLSB, it's at 4.5. And the fifth is shifted to the left by half VLSB, it is also at 4.5. Okay, so in fact it looks like it is jumping from here to there. It has a jump, much larger jump. Okay, and again sixth one is slightly earlier than what it should be, the seventh one is slightly later than what it should be. So this kind of things can happen because nothing is ideal. I want to establish thresholds at VLSB, 2 VLSB and so on. but they can all be shifted around by some amounts. Okay. So the transition points will be shifted from the ideal values, and this gives rise to some errors, which are known as the gain error, the integral nonlinearity, and the differential nonlinearity. Okay. So let me go through the nonlinearities. So I can go back to this. So first of all, what will happen if let's say this, as the curve showed, so let's say instead of the red, which was the ideal curve, we have the black. So what is the result of that? Why are we even worried about it? Error will be? That's correct. So before, the error was in a range VLSB, 0 to VLSB. Okay. Now, what is this error defined as? Vn minus the digital output times VLSB. Okay. How will that change? How will it change? What will be the change value? So for the ideal case, I have already drawn it here. Okay, maybe I will draw it in red to. So the red characteristic was the ideal case, and Vn minus d out time VLSB follows this curve. The black characteristics here are the non-ideal case. What will happen to this? Just help me draw this curve. So let's go through from the beginning. At 0, what is the error? 0. Okay. Now what will happen as I increase the input from 0? It follows the input, and the location of the jump in the characteristic has shifted to the right. So the location of the jump in VQ also will shift to the right. Okay. So I will get something like this. Okay. And what happens after that? Again follows the same curve, right? And what happens after that? Where will the next jump be? Before the ideal value. Okay, at this point. And the next jump. So between jumps it follows the same curves. Okay. And the location of the jumps has changed because the transition points have changed. So the next jump, because the next transition point is at the same value, it happens to be at the same value, it will be there. And the next one, it will go up, comes down where? Comes down here and then goes up. We are looking at this particular jump, right? See, here there are two jumps together coinciding. So it jumps once and jumps again. And then it follows this one. It does this, does this. Okay. So we have this blue curve instead of the red curve. So, okay, what is the result? Okay, it is different, that I know, but what is the problem? Exactly. The range is more than 1 VLSB. Okay, that is the problem. So far along, we said that the range of the quantization error will be 1 VLSB. It was minus half VLSB to plus half VLSB or something like that. Now the range has become more than 1 VLSB. Okay. Now this is because we were not able to place the transition points accurately. Now, why exactly that may happen, we will see later, but generally you will not be able to place the transition points exactly where you want them to be. Okay. Now, this error is a different type from quantization error. That quantization error, everything was ideal. Still you are getting error simply because of the rounding process. Now, this is because of my inability to make the transition points. So, this is an error in the design or some kind of non-ideality in the design. Okay. So, the result is because of the shift in transition points, the range of the quantization error increases. Okay. Range of VQ with non-idealities. Okay. Now, how much range is acceptable? This very much depends on the application. Okay. Now, typically, when you have no further information about the specific application, we say that the range of VQ can be 2 times VLSB. Okay. So, what this means is the following. If I made an ideal quantizer, I would have got a range of VLSB. Okay. Now, I know I can't make an ideal quantizer, there will be some more errors added to it. So, how much error to allow? I will say that I can at most double that error. Okay. What was VLSB? The range, it can become 2 times VLSB. Because of my errors in design, because of the errors in my design, the range of VQ has increased, and I let it increase up to 2 VLSB. Okay. Otherwise, I will not be able to design it at all, but no more than that. Okay. So, that is my definition. Okay. So, inherently in the quantization process, there is some error, and I will allow myself some more error so that I am able to design it at all. And I will allow myself exactly the same error that is inherent in the quantization process. Okay. So, this is the typical definition, but this is not universally true. Maybe when you actually design an A2D for a specific application, you may be able to tolerate more, or you may have to tolerate less. Okay. But this is a number. In absence of any further information, you can use this to be the number. Okay. So, the black is the ideal characteristic and red is the non-ideal characteristic. Now, we have to define the errors also. I just said the errors can be less than 2 times VLSB. There are different types of errors that can be defined. So, what is the bottom line? The quantization error has increased. So, what will that do to our A to D conversion process? Not alias error, the quantization error has increased. Okay. Before, the energy in the quantization error was VLSB square by 12. Now, clearly it will be more because it is distributed over a higher range. Okay. But I will limit it to 2 VLSB. So, hopefully it is limited to some reasonable extent. Okay. Now, there are different errors that can be defined here. I mean, the error can be described in different ways. One is, so we know that the ideal transition points must be here, here and so on. I mean, at 1, 2, 3, 4 VLSB. The actual ones have shifted around. So, one way of determining the error is to see simply the difference between the transition levels. Okay. So I will plot that above this. Okay. So the first one, the first actual transition is beyond the ideal transition, so that constitutes a positive error. I'll take this difference, okay, and plot it here. That is somewhere here. The second transition is negative. It has a negative error, okay, that I'll plot here. And the third one has zero error. It happens to be zero error, so I'll plot that here. And the fourth one, actually I have chosen half VLSB error. Okay, it's exactly at midpoint. So at fourth one it is plus half VLSB, and at fifth one what is it? Minus half VLSB. Oh, sorry, not here. Next one is minus half VLSB, and the next one is slightly negative, and the final one is slightly positive. Okay. So this is the difference between actual and ideal transition levels. Okay, is basically the difference between the characteristics that you want and characteristics that you get, and this is known as the integral nonlinearity error. Okay, or INL error for short. Okay. This is INL, and if you take a typical A2D data sheet, you will see this INL, and that's what this means. The transition points have been shifted around. How much it is shifted is given by this one. Okay. And the INL can be both positive and negative. What is the maximum value of INL you can tolerate? I already said that I will tolerate. So VQ ideal goes from 0 to VLSB. Okay. And I want the VQ real to have a range of two times VLSB. Okay. From this, can you say how much the INL should be? What is the maximum value of the INL? Remember, INL can be both positive and negative. Okay, you don't know. Plus minus 1 LSB. Okay. Can it be plus minus 1 LSB? See, this is the. You can go minus 2. No, this is the range of. See, even in the ideal case, there is a quantization error which has a range of LSB, VLSB, right? VQ has a range equal to VLSB. Now, in the real case, it has a range of 2 VLSB. That's my error. So, how much can the INL be? While keeping in mind that INL can be both positive and negative. VLSB? Okay, let's see what happens. In this particular case, for fourth level, what is INL? VLSB. What is INL? plus VLSB by 2, right? So INL here is half VLSB. For the fifth level, what is it? Minus half VLSB. Okay. And I have drawn the same thing here. What is this point where it starts changing, where it jumps? Yeah, what is this point? So this 3 by 2 VLSB. Okay. It will, see, normally it would have built up to 1 VLSB. It goes half VLSB beyond that. So it is 3 by 2 VLSB. So the maximum value in this case is 3 by 2 VLSB. And what is the most negative point? Minus half VLSB. So what is the range? 2 VLSB, right? And what is the INL in this case? It's for the same curve, right? What is the maximum value of INL? What's the maximum positive? What's the maximum negative? Plus minus 0.5. So that is what you can limit it to. You can't have plus VLSB or minus VLSB error. Okay, because this particular step here has a plus half VLSB error and the next one has a minus half error. Okay, we can't say which one has how much error because that depends on the design and it's randomly distributed. We can only put a limit to what the maximum is. So it could be that one level has a plus half error and the next level has a minus half error. What will happen? Suddenly you will get a jump of 2 VLSB. That means that your quantization error range is 2 VLSB. Right. So you can only allow a maximum of half VLSB error. That's what it means. Okay. So if I limit my error, quantization error to 2 VLSB, my INL has to be, the magnitude of the INL has to be less than half VLSB. Now you don't know whether the INL will be positive or negative for a particular code. Okay. Is this clear? If you draw the characteristics, this will become very clear. So have you seen this criteria somewhere that INL has to be less than half VLSB? No, you have not seen it? Okay. So that is typically what is taken to be the assumption. Okay. Now you can't say I made a 16-bit converter and give a converter which has an INL of 1000 VLSB. Okay. Then it's not a 16-bit converter. If a converter has a certain VLSB, it means that you can resolve the level to some error. Ideally it is a range of 0 to VLSB. In reality, it will be more. And I have put my limit to be 2 times VLSB. Okay, it has to be something like this. You can't have 1000 times VLSB because nobody will, it's not be credible, right? Now, if you want to have this much error or less, your INL error should be less than half VLSB. So that means you should place all these comparison levels at the desired values plus minus half VLSB. Okay. Is okay? Now there is another type of error which can be defined. That is, you look at the flat portions of these characteristics. In the ideal characteristic, how wide is this flat portion, the first one? How wide is the first? This is just this flat. It's basically a succession of steps, right? What is the width of each step? In the ideal, 1 VLSB. Okay. In reality, what is it? It is different. Okay. So we can define the error to be the difference between the step widths. Okay. And this is known as the So the first step is wider than ideal, that I will call as a positive error, and the second step is much smaller than ideal, so that will be a negative error, and the third step is no, is it? What is the width of the third step? Is more than ideal. Okay. We are not looking at the location of where this is. We are only looking at the step sizes. Okay. The step width. And the fourth one is how much? Huh? It is more. Exactly how much is it? So this is at 4.5, right? So how much is the DNL? Half VLSB, right? We are looking at the difference between the actual width and the ideal width, and that is half VLSB. Next one is minus half, and sorry, the next one is not minus half, that is the width of this minus 1, which is slightly less than minus half. Okay. And similarly, the next one looks like it is more, and the next one is probably less. Okay. So you will get some errors like this. Yeah. Fourth one is minus 1. Yeah. Yeah, isn't it the step width? I think DNL less than minus half may give a slipping code, missing code, but not necessarily. No, I have plotted the difference between the actual and ideal. Yeah. Oh yeah. Yeah. Okay. So this is the first, second, third, fourth. Maybe the fifth is missing, right? So, yeah. So actually, yeah. Let me redo this thing. So there is a double step here, and one of the levels is completely missing. Okay. Actually, first of all, I should have probably removed the offset. I think otherwise. So the way it is normally plotted is, this is plotted for 0. Okay. So that for now I will say is positive. This width is more than what it should be, and the second one is smaller, so it should be here. And the third one is, ideally it is this much, actual it is this much, so it is positive. Okay. So this you can imagine to be something like this, and it has a 0 step here, 0 size step here, and then jumps up again. Okay. So the next one is, this is larger than what it should be. Okay. So it is plus, happens to be plus half. The fourth one is, the ideal is 1 and the actual is 0. Okay. There is no step there at all. So it is minus 1. Okay. So that's what actually I was trying to point out, then I missed something. Thanks. This is minus 1 VLSB. Okay. And the next one is maybe slightly positive, and the next one is also slightly positive, and so on. Okay. Is this okay? So here we get minus 1 VLSB, because one step is completely missing. Okay, there is a double step here. So basically, you can say that for the step in the middle, the width is 0. Okay. So that is known as a missing code error. So that is, For no value of the input, will you get an output of 4, right? As you increase the input, it jumps from 3 to 5 directly. Okay. Now this is also a typical, this is a property of the missing code, that when you have a missing code, the DNL will be minus 1 VLSB. Because the ideal step is 1 VLSB and the actual step is 0. So the error will be minus 1. Okay. So this is the differential nonlinearity error. This is basically like the local error. Every step, how much it is, it tells you. Okay. And if this is larger than 1 VLSB, it means that your quantization step is larger and you will have more errors. Okay. And this DNL is also typically limited to half LSB in magnitude. Okay. So if you do this, you also guarantee no missing code, because for missing code, DNL will be minus VLSB. Okay. So this is the differential nonlinearity error. Okay. So there are other errors like gain and offset, which I won't go through now. Maybe we can review that later, because this has taken quite a long time. But it is all related to, the gain and offset are related to the error in the very first step and the error in the last step. Okay. We'll take care of that later. But the main types are this integral nonlinearity error, which says where the transitions are with respect to the ideal positions, and differential nonlinearity error, which tells you how much each step, how wide each step is compared to the ideal values. Okay. Any questions on this? These are definitions, but these are things that you need to know again when you model or simulate your A to D converter. So this I will skip for now. So the last two are what I covered. INL is the deviation of transition points from ideal, and DNL is the deviation of intervals from the ideal values. Okay. Now finally, when you put in a sine wave to this A to D converter and you measure the output spectral density, you will get some quantization error, and also you may get some harmonics. Okay, just like you get in an amplifier. Okay, this happens because of various non-idealities in the A to D converter. When you simulate it, you see it. And there are measures of non-linearities which define how much those errors are. Okay, just like we said DNL and INL, but these refer to static. These are called static non-idealities, because you keep the input fixed, you vary the input slowly and see where the outputs change, and then based on that you calculate the INL and DNL. Whereas you put in a sine wave of some frequency and then test how much the errors are, those are known as AC non-idealities. Okay. And again, this I won't go through the details now, because you will not be able to appreciate this unless you simulate something. But there is something known as SNDR, which refers to the signal to noise plus distortion ratio. That is basically the ratio of signal to every other frequency component. Okay. You have signal energy, energy in all the other components. That is SNDR. Okay. And the signal to noise ratio is in the output, you will see something which looks like noise and something which looks like harmonics or other discrete tones. You exclude the discrete tones, take only the noise, that is signal to noise ratio. Okay. So these things I will come back to when we deal with FFTs and looking at the signals. But for now I will just mention these things. And similar to amplifiers, you have second harmonic and third harmonic distortion. Okay. Which you specified. Okay. But remember that all of this is done on the digital output signal, not on the analog, not on any analog signal. Okay. So any questions so far? These are the basic definitions of the A to D converters. The main non-idealities that you need to keep in mind are DNL and INL, and there is some related stuff with offset and gain which we will deal with later. Okay. Any questions?